Thank you. Thank you for inviting me to give this talk. So this will be a rather different topic than the previous talk. And actually, it will be about geometry of numbers, and I take the opportunity for people attending in line. I take this opportunity to make the precision that we are here in the amphitheatre Claude Chaboty, who made important contributions to geometry of numbers. What I want to do is to describe the so-called Voronoi Complex, which has proved to be useful for computation in homology and cohomology of groups. But before describing this complex, which will be the topic of the second lecture, I would like to explain where it comes from. So the Voronoi complex relies on the concept of perfect quadratic form or perfect lattice. And in fact, this concept of perfect lattice or perfect quadratic form has its roots in a problem, a very classical problem in geometry of numbers. That is the question of the search for dense lattice packets. And it turns out that these perfect lattices or perfect forms, which are the zero cells of the Voronoi complex, are somehow the critical points for the density function associated to a lattice packing. So that's this aspect that I will tell about in the first lecture. And so to start with, I will. I hope the talk is completely self-contained. So I assume zero knowledge of anything. So in principle, it's completely elementary, maybe too elementary. I don't know. You will tell me. So a few words and notation about lattices in Euclidean space. So a lattice is just a closed discrete subgroup of maximal rank, or said differently, this is a group consisting on the linear combination with integral entries of vectors of bases of R to the n. So take n linearly, the integral linear combination of the vectors of any basis of R to the n. And so you fix an inner product on R to the n, say the usual one. So associated to that, there is a notion of length. And also, and that's how quadratic forms come into play. To a given matrix, you can associate its gram matrix. And the determinant of this matrix is what one calls the determinant of L. It does not depend on the choice of a basis, of a Z basis. And it's it measures, it is equal to the square of the volume, or the co-volume of the lattice. That is the volume of any fundamental domain for the natural action of the lattice on the ambient space by translation. So those are the basic notation I will I will use. So an important notion is a notion of the minimum of a lattice, which is a minimal distance between pairwise distinct elements in the lattice. And so these two quantities, the minimum of L and the determinant of L, will appear in the next slide as a way to measure the density of the sphere packing associated to the lattice. So this is, I think, very well known, but I recall what it means. So first, I recall what I mean by sphere packing in general. So it's just a collection of non-overlapping spheres of equal radius. And to such packing, one can try to associate a density. So this density does not always exist. It depends on how random your distribution. Sorry?
One question on Zoom. Do you need to take the absolute value of the determinant to make sure it's positive?
The way it is defined, the inner product is a positive definite quadratic form. So if the determinant of the Gram matrix is positive. Okay. So there is no need for the absolute value. So to evaluate the density of such a packing, you just compute the size of the intersection of your packing with a big ball of R. Say R. Where is the pointer on this thing? I don't know.
The second from the
this one. Yeah, thank you. And then you evaluate the ratio of space you get by taking the intersection and take the limit as the radius grows. And if it exists, this represents the density of your packing. And it turns out that in the case of regular packings, packings associated to lattices, this density exists. And as you see, it is essentially computed by this ratio, which involves the minimum of the lattice and by the determinant. So although this is very classical and well known, I just give a kind of sketch of proof of this. The point, so well, just to explain how this quantity appears, the point is that everything boils down to the fact that essentially to estimate the density of the packing, you just have to look to what happens around a given point of your lattice. And namely, one defines the Voronoi cell of a point of the lattice as a set of points which are closer to X than any other point of the lattice. So this is, in this figure, the blue hexagon here, the inside of the blue hexagon. And it turns out, I will give some detail on the next slide, that the density of the wall packing, in fact, is well approximated by the ratio of the volume of this sphere, of a single sphere, by the volume of this Voronoi cell. And that's it, essentially. And this explains completely this formula. There is nothing mysterious, except that you have to do the computation. So maybe I will be rather quick on that because this is not the main subject of this talk. But if you want some details, here they are. So the sphere, the red ball here is the ball of radius r, with radius r which is meant to tend to infinity. And it turns out that it's very easy to see that essentially to estimate the density as r tends to infinity, it's enough to take the ratio between this gray, the volume of these gray spheres and the corresponding Voronoi cells, because what you the part that escape from this computation is irrelevant as r tends to infinity. So that's for the explanation for this formula. Nothing deep here. So this motivates the definition of the Hermit constant. This after a suitable normalization, the density of a sphere packing associated to a lattice is completely determined by this quantity, which we call the Hermit constant of L. And the maximal density in a given dimension is what one calls the Hermit constant in dimension n. Okay, so as I will recall in the next slide, not much known about the actual value of this constant. There are anyway some known results about the asymptotic behavior of n, which I summarized in this statement. So as you see, there is a gap between the left-hand side and right-hand side, which is rather mysterious. And just to say a word about the state of the art regarding this question, the left-hand side actually is Minkowski-Lafka theorem, which is rather old, as you see. And there have been recent but rather modest improvements on this, which I mentioned a few here. The most recent one is due to Askai Venkatesh 10 years ago. And the right-hand side, the best upper bound to date is due to Kabatiansky and Levenstein. And there are, I forgot to mention some recent improvement, but not in the asymptotic range, but still some improvement by Elkis and Cohn, some 15 years ago. Okay, so that's for the underlying story of Hermit constant. And now the perfect forms and lattices will come into play. Just before that, I just summarized what is known about which actual values of the Hermit constant are known. So only a few, as you see. With this surprising gap you certainly noticed, and which I won't comment upon today, between, so you see everything is done up to dimension 8, almost nothing between 8 and 24, and there is this miracle in dimension 24, which was proven by Cohn and Kumar in 2009. Okay. questions so far, because I will move to something rather different. No? Okay. So now I will explain Voronoi theory, which is a characterization of the local maxima of the density function I've just defined. And it turns out that the theory is easier to explain in terms of quadratic forms. So far I mainly spoke about lattices, but I will switch to a different language. And there is a kind of a dictionary between two worlds that I will explain in more details in the next slide. So on the one hand, you have the set Ln of Euclidean lattices up to isometry, because of course two isometric lattices give rise to isometric packing, and in particular they have the same density. So this is perfectly natural to consider lattices up to isometry. And on the other hand, we already saw how to associate a quadratic form to a lattice just by considering the gram matrix of a given basis. I will recall that in the next slide. And then there is a different equivalence relation to take into account, which is that we will consider positive definite quadratic form up to integral equivalence. And that's where the application to cohomology of a group appears first, because what we will build in the next talk tomorrow is a GLNZ invariant tiling of this cone of positive definite quadratic forms. This is what I will explain tomorrow. And just to make things as precise as possible, since I will use this notation all the time from now on, I recall what the action of GLNZ is. So I let GLNZ act on the set Sn of R of real symmetrics n by n matrices. In this way, by taking the product U transpose times A times U, which I will abbreviate with this classical and standard notation. Okay, so this is the way GLNZ acts on this situation. And as I already mentioned, the density of two isometric lattices are the same, of course, which allow to view the density on the set Ln modulo the orthogonal group. And the set Ln itself can be viewed as a homogeneous space in that way. Yes?
Two quadratic forms have equivalence if they are in the same angles?
Yeah, yeah. I will maybe restate that later on that slide. And this double quotient in the middle, you can rewrite it as the quotient of the cone Pn of positive definite quadratic form by the action of GLNZ I've just mentioned. So to be more precise, how this identification work, there is a misprint, so there is no, it's okay. I couldn't read, but it's okay. So to a double coset here with representative G, you associate on the one end the corresponding lattice, namely if you see J as a matrix, you take the lattices generated by the column of J, and on the other hand, you consider on the right-hand side, you consider the positive definite quadratic forms defined by this product. So this is how the dictionary between lattices on the one end and quadratic forms works, and positive definite quadratic forms work. Stated differently is just the association I mentioned in the first slide, namely a given lattice equipped with a chosen basis, you consider the corresponding gram matrix. This is exactly the same thing as stated differently. And yeah.
The Zoom request.
Yeah.
Question. Could you repeat the question, because the Zoom audience didn't know.
Oh.
They didn't hear the question. They heard your answer.
Yeah. So the question was what means the integral equivalence. So I was just asked to precise when two quadratic forms are considered to be integrally equivalent. This just means that they are in the same orbit under this action of GL and Z. So that was the question. Okay. So to summarize, I wrote this little where on the left you have all the notion from the point of view of lattices, and on the right-hand side, the corresponding notions in terms of positive definite quadratic forms. So in particular, you can define the minimum of a positive definite quadratic form as the minimal value it achieves on non-zero integral vectors, and this corresponds, of course, to the minimal length of the corresponding lattice. And for some reason which so far will seem obscure but will become clear in the next slide, I also mention this correspondence. So on the side of lattices, we will consider tensors of this shape, which will correspond to matrices of a spatial shape in the set Sn of symmetric matrices defined associated to a given vector x. So this will play an important role in the definition of perfect forms in the next slide. So I think that's it. So associated to a lattice, there is a well-defined finite set of minimal vectors, and corresponding to that, on the side of quadratic forms, you can define the set of minimal vectors of a positive definite quadratic form. And precisely, as I was mentioning before, to a vector x. So for me, vectors, unless otherwise stated, will always be. I lost. Here it is. Vectors will always be column vectors, so that when I write the product x times x transpose, I get this matrix, which of course by construction is a symmetric matrix, But it's not a positive definite symmetric matrix because it's very degenerate. It's highly degenerate because it is a rank 1 symmetric matrix by construction. But it's on the border of the positive definite cone. So these objects will be the basic objects to define Voronoi domains and perfect forms. So here is the definition of the Voronoi domain of a quadratic form. So here in this definition, A is any positive is a positive definite quadratic form with no restriction so far, and its Voronoi domain is the conic hull in Sn of R of these matrices Q of X associated to the minimal vectors of A. So you start with a positive definite matrix A. You compute the finite set, its finite set of minimal vectors, and for each of these minimal vectors, you compute the matrix Q of X, this rank 1 symmetric matrix, and you take the conic hull of this finite set of matrices. And this is what is called the Voronoi domain of A. So just to have a picture of what it means, so this is a cone of positive definite matrices in the case, of course, for a small n, for n equals 3. So here in red, I draw two rays corresponding to, say, two minimal vectors. Okay, so those are the Q of X or Q of X1 and X2. And so in that case, assume, for instance, that you are working with a quadratic form which has only two minimal vectors. Then its Voronoi domain will just be this triangle, so which I cut off here with this plane section, but you imagine can imagine it as an infinite cone. And if there are more minimal vectors, like in this situation, then this conic hull will look like this kind of polyhedron. Okay, but keep in mind that in general, the Voronoi domain of a quadratic form will certainly have a lower dimension, like in this case, and it can even be the case that there is only one minimal vector, and this is a generic situation in a sense. So where there is only one minimal vector, then the corresponding Voronoi domain just consists on a single ray. Okay. Okay, and so what we will see now is that there is a way to characterize the local maxima of the density using this Voronoi domain. So to that end, I need two more definitions. So the first one is the definition of a perfect lattice or quadratic form. So just to summarize what you can read on this slide, I will just keep the third version, which is that a quadratic form is perfect when its Voronoi domain, as defined before, has a maximal dimension, which I can formulate by saying that it has non-empty interior. So for instance, in the previous slide, this one is perfect in this situation. It has a non-empty interior, but this one is not because it has an empty interior. Okay, so this is the definition of the Voronoi domain. An obvious but important remark is that a perfect lattice necessarily has got quite a lot of minimal vectors, at least the dimension of the SNR, and also an important remark, which is that the motion is invariant under the action of GL and Z. Okay, so a few examples just to see what it means in concrete terms. So here is the classical hexagonal lattice A2. So I claim that this one is perfect, which you can check just by computing the matrices Q of x1, x2, and x3, having first computed the minimal vectors, which are these 3, 1. Also, they are opposites, but they give rise to the same form in the space of symmetric matrices. And clearly, these 3 matrices span the whole space of 2 by 2 symmetric matrices. So this lattice is perfect. While this one is not, just because it doesn't have enough minimal vectors. It has only 2 minimal vectors, and we need at least 3 from the previous remark, because here the dimension of the symmetric space is 3. Okay. The second definition I will need before I can formulate a Voronoi theorem is a notion of eutactic lattice or form. And again, so I wrote down 3 equivalent characterization. And here I will concentrate only on the third one, which is that a quadratic form is eutactic if its inverse lies in the interior of oh, I made a mistake here. It's not the interior, it's the relative interior. It's a misprint I have to correct. So A is eutactic if the inverse of A lies in the relative interior of the corresponding Voronoi domain. By a relative interior, I mean the interior in the affine generated by the minimal vectors of A. So if the above equivalent conditions are fulfilled, one says that A is eutactic. Okay. So I won't say much about eutactic forms, neither today nor tomorrow, because eutactic forms don't play. Well, I shouldn't say that they don't play any role in the Voronoi complex, because actually they do, but it's secondary. So I won't insist too much on eutactic forms. But they will play a role in the formulation of the Voronoi theorem. Just before I formulate a Voronoi theorem, I also give 2 examples. So as before, if I consider the hexagonal lattice, then it is eutactic. It is a simple computation to check that the inverse of the Gram matrix corresponding to the hexagonal lattice here can be written as a linear combination with positive coefficient of the Q of Qx1, x2, and x3. Just a computation. And contrarily to what happened with perfection, the Z2 lattice is eutactic as well, because again, it's a simple computation to check that the inverse of the identity matrix, which is the identity matrix, can be written as a sum of these two rank 1 symmetric forms. Okay. So, what do we do with these two notions? Well, these two notions show up in this old theorem by Voronoi, which says that a lattice or the corresponding quadratic form achieve a local maximum of density if and only if it is perfect and eutactic. And my aim in the next, say, 10 or 15 minutes was to give a sketch of proof of this theorem because it's, well, as you see, it's rather elementary, but it's not so easy to find a complete proof. I mean, of course, you can refer to Voronoi paper, but it's written in a old language. So I thought it was maybe not useless to give a sketch of proof of this theorem. Okay, and also the proof itself will be the occasion to introduce some features of the space Sn, which will be very important in the actual description of the Voronoi complex tomorrow. So the first of these geometric features I wanted to introduce is the scalar product on the set of n by n symmetric matrices. Namely, one can define the scalar product of two matrices A and B, symmetric matrices A and B, as a trace of their product. And there is the following completely elementary but essential remark, which is that when you consider this scalar product with A being any quadratic form and B being one of these rank 1 symmetric form associated to a vector, not necessarily integral, by the way. Here I do the computation for an integral vector, but it works for any vector. Product is a trace of the product of A by this product X transpose. And by elementary linear algebra, this trace here is the same as that one, except that here you see the objects here and there don't have the same dimension. Here you have n by n matrix, and here you end up with a 1 by 1 symmetric matrix that is a number. So this trace is nothing else than this evaluation of A on X. So really the key point in Voronoi theory, including the construction of the Voronoi complex, is this obvious observation that the evaluation of a quadratic form on a vector X can be thought as the scalar product of the matrix A with the corresponding matrix Q of X. This is really a key point in all the theory. And another key property is that the association of the set of minimal vectors of a given form is locally decreasing, meaning that starting with a given positive definite quadratic form, if you move in a sufficiently small neighborhood of A, of your initial matrix, the set of minimal vectors can only decrease and stay inside the set of minimal vectors of the initial form. In particular, it cannot increase. So those are the two main tools. Actually, there is a third tool that I will mention in the next slide, and these third tools will be enough to prove the theorem. So this is a if and only if. So there is two directions. So I will first prove that if A is a local extremum for the density, then it is perfect and eutactic. So why is it true that locally densest lattice packing give rise to a perfect quadratic form? Well, assume by a way of contradiction that it is not the case, then you can find a non-zero symmetric matrix, which is orthogonal to every minimal vector. And this means that when you evaluate the form A plus TH, whatever T, on a minimal vector of A, then the value you get is the same as the value of A on the same vector. And as we know that locally the set of minimal vectors can only decrease, it means that for small enough T, the set of minimal vectors of A plus TH will stay identical to the set of minimal vectors of A, and the minimum of A plus TH also. And then, and this is the third, the third ingredient, using the log concavity of the determinant, you can realize, this is a small exercise, that for suitable T and small enough T, either positive or negative, depending on the situation, the determinant of this matrix has to decrease, which means that since in the density the determinant appears in the denominator, it means that the density has to increase since the minimum stays the same. So this is that simple. So that is why we have this. And as for eutaxy, it's a little more complicated. So I don't. Maybe I will be more sketchy on that part. But except that this is the first occasion for me to define facet vectors, which will play a prominent role in the construction of the Voronoi complex. Let us comment a little bit on the picture rather than commenting the computation on the left-hand side. So here I've drawn the Voronoi domain of a perfect form, and to each of its code dimension 1 faces, I associate a facet vector which is directed inward, so towards the interior of the domain. This is the convention I use. And if ever A were not eutactic, this would mean that this scalar product would have to be non-positive for at least one of these facet vectors. And again, so this would mean that the derivative of the determinant in this direction would be negative. And again, if you combine that with the log concavity of that of the determinant for the same reason as before, this would imply that the determinant decreases for small enough positive T, and so the density has to increase because the minimum remains the same. Okay, so those are the ingredients, which, as you can see, are completely elementary. So there now comes a reverse implication. And since I'm kind of running out of time, I choose to write it very, very small. You don't want to see the details. Well, it's the part that in many references I know is kind of unclear. So I stick to the tradition. So I keep it rather mysterious. But well, if you are able to read this, if it's not too small, here you have a full justification of the reverse implication. And to be to give a complete reference, this proof actually is due to Martin Kneser. Martin Kneser, who wrote many papers in the algebraic theory of quadratic forms, also wrote a paper in the 50s on a new demonstration of Voronoi theorem, and this is, to my knowledge, the best place to read at least this implication of Voronoi theorem. So I won't insist on that part, but okay, just to say that the equivalence is perfectly correct. Okay, so so in the same paper, Voronoi also showed that up to GL and Z equivalents, there are only finitely many perfect forms. So that in principle, if you are able to classify this finite set of perfect forms in a given dimension, then you are able to compute the local maxima of density in a given dimension, and ultimately you will find the Hermit constant in the corresponding dimension. You will see in the next slide the technical complication that appear when you try to apply this strategy. As for eutactic forms, so the finiteness result for perfect forms is in fact rather easy to prove. It's a matter of classical reduction theory. It's obvious. As for eutactic form, it's also true that there are only finitely many up to GL and Z equivalents, but it's much more complicated to prove. And all proofs I know all relies more or less on topological argument, and the first who proved this was Avner Ash in 1977, using the fact that the density function is a topological Morse function on the set of positive definite form modulo integral equivalence. Okay. And well, although I say that I would not insist on that, this is one important feature of the theory, which is that this eutactic form corresponds to critical points of this topological Morse function. Okay, another important consequence of Voronoi theorem is that the perfect forms and also the extreme forms have to be proportional to rational forms, forms defined over Q, which is not the case for eutactic forms. There are counterexamples already in dimension 4. And here is what is known about the classification of perfect forms in low dimensions. So as you see, the situation becomes incredibly complicated after dimension 7. And in dimension 8, the full classification was obtained only rather recently by Mathieu Dutour, Achille Schurman, and Frank Valentin. And as for dimension 9, as far as I know, there is a work in progress by Mathieu Dutour and Wessel van Woerden. And it seems that there are billions of perfect forms in dimension 9. That's it. Okay. Just a few words about the references for this third part. So, of course, there is the original paper by Voronoi. You can find details also in the book by Jacques Martinet on perfect lattices. If you are interested in sphere packings in general, you are strongly advised to have a look to this book by Conway and Sloan, known as the Bible of the subject. And finally, I put here the reference to the paper by Martin Kneser that I mentioned before, because I think that this paper is not so well known. And you see it's a very short paper, which contains a very nice proof of the theorem I've explained today. So maybe it's a good place to stop, and tomorrow I will explain the construction of the Voronoi complex.